In this video, we're going to talk about the fundamental theorem of calculus. It comes in two parts. Part 1 tells us how to create a new function from an integral. So part 1 tells us that if we start with a continuous function on the closed interval from a to b, then we can define a new function, also defined on the closed interval from a to b, simply by integrating the function f from a to any point that is between a and b, which we're calling x. So we're allowing the upper limit of integration to vary here. This defines a continuous function on the closed interval, which is differentiable on the open interval, and what's even more amazing is we know the derivative of this very strangely defined function. Namely, it's simply f itself, which tells us that differentiating undoes integration. Part 2 is really a corollary to part 1. So part 2 tells us how to evaluate indefinite integrals using part 1. So if we have a function f that is continuous on the closed interval, it satisfies the hypotheses of part 1 of the fundamental theorem. Part 2 tells us that if we can choose any function that we like, capital F, so that its derivative is equal to f on the open interval from a to b, then the integral, the definite integral from a to b of little f is big F minus big F evaluated at b minus big F evaluated at a. So this is an important piece. So we're going to do the proof for part 2. So first of all, by part 1, we already have a function which satisfies the conclusion of part 2. The function g, which is defined by integrating f from a to x, has its derivative equal to f. So we can check that when we plug b into g and a into g, we'll simply get the integral from a to b of f. So we observe that g of b is by definition the integral from a to b of f. G of a, on the other hand, is the integral from a to a of f, which we know from the previous section is 0. So if we subtract 0 from the integral from a to b of f, we just get the integral from a to b of f back. So the other part of the fundamental theorem, part 2, is that this formula works for any function that you choose that satisfies capital F prime equals little f for all x values between a and b. So to finish this off, we have to recall corollary 3.27. So corollary 3.27 told us that if we have two functions that have the same derivative, then they differ only by a constant. So if capital F is some function whose derivative is little f, then g, which we defined above, which was also a function whose derivative is equal to f, those two things have to differ by a constant. So if we plug b into capital F and a into capital F and take the difference, we'll see that we'll get g of b. So we see because these two things differ only by a constant, when we plug b into capital F, we get g of b plus that constant. F of a is g of a plus that same constant. So since g of a was 0, that's the integral from a to a of f, the two constants will cancel out. We're left only with g of b, and that's the same thing as the integral from a to b of f. And we're done. So if we're interested in evaluating definite integrals, then we should have a name for functions like capital F. So we call a function like capital F an antiderivative for little f on the open interval I if the derivative of big F is equal to little f for all values of x in that open interval. Here are some examples. So for any number n that's not -1, if we take the derivative of 1 over n plus 1 times x to the n plus 1, we'll get x to the n, which tells us that 1 over n plus 1 times x to the n plus 1 is an antiderivative for x to the n. This is true for the whole real line, so we simply say x to the n plus 1 divided by n plus 1 is an antiderivative for x to the n. This tells us that if we want to integrate a power of x, all we have to do is evaluate this antiderivative at the two limits of integration. So we use this bar with the lower limit a and the upper limit b at the bottom and the top respectively to indicate that we're evaluating the function x to the n plus 1 at b, then at a, and taking the difference between the two. This is a nice shorthand. So combining the properties for the definite integral from our last video with this new technique, we can now integrate polynomials very easily. This says that if we want to integrate a polynomial, all we have to do is integrate each of the pieces one by one. To integrate each of these monomials, we only need to find a single antiderivative. So to do this, we can increase the power on x by 1, and then divide by the new power for each one of the terms. So the antiderivative of an x to the n is an divided by n plus 1 times x to the n plus 1. The antiderivative for an minus 1 x to the n minus 1 is an minus 1 over n times x to the n, etc. down the line. The antiderivative for a1x is a1 over 2x squared, and the antiderivative for a0 is a0x. So to evaluate the integral from a to b of our polynomial, we just have to plug the numbers a and b into this antiderivative, then take the difference. So here's a quick example. So here we integrate each of the terms individually. I increase the power on x by 1 to get x cubed, divide by the new power, so my coefficient is 1. When I plug in 2 and 1, I'll get 2 cubed is 8, minus 1 gives me 7. For the next term, increase the power by 1, I get x squared, divide by the new power, my coefficient is 1. 2 squared minus 1 is 4 minus 1, gives me 3. 7 times x, evaluated from 2 to 1, is 7 times 2 minus 1. That gives me my minus 7. The 7's cancel out, and we get 3. So this tells us how to integrate all polynomials very quickly without having to use Riemann sums, which is very nice because Riemann sums are quite cumbersome. The other set of functions that we know about are trigonometric functions. So we know all the derivatives of the trig functions, so that's going to give us our antiderivatives. Cosine is nice and easy. The derivative of sine is cosine, which tells us that sine is an antiderivative for cosine. So if we want to integrate cosine from a to b, we just evaluate sine of b minus sine of a. Sine is a little bit trickier to integrate. Because the derivative of cosine is not sine, but minus sine, the antiderivative of sine is actually minus cosine. So that tells us if we want to integrate sine from a to b, we have to take negative cosine of b minus negative cosine of a. For secant squared, we can see the derivative of tangent is secant squared, gives us our antiderivative. So the integral of secant squared from a to b is tangent of b minus tangent of a. Secant of x is an antiderivative for secant x tan x, since the derivative of secant x is secant x tan x. So integrating from a to b secant x tan x, we get secant b minus secant a. So just like with sine, cosecant squared has a trickier antiderivative. The derivative of cotangent is not cosecant squared, but minus cosecant squared. So the antiderivative for cosecant squared is negative cotangent. So we have that the integral from a to b of cosecant squared x dx is negative cotangent b minus negative cotangent a. The same sort of thing will happen for cosecant cotangent. Again, the antiderivative for cosecant cotangent is negative cosecant. So the integral from a to b of cosecant x cotangent x dx is negative cosecant b minus negative cosecant a. So this gives us our entire list of antiderivatives and all of the functions that we currently know how to integrate using the fundamental theorem of calculus.